Hi, everyone.
Hi.
Yeah, I'm not recording. I always stop it to take the quiz, but it's okay. We haven't really done much. Okay, so what's the oxidation half for that first one?
SR.
Mm, mm, mm.
SR.
Gonna be negative E.
But 2SR,
Yeah.
right? 2SR, not just SR. So this is the oxidation half. So where do the electrons go? On what side of the reaction?
Left.
Mm,
Right.
Not on the left. Oxidation means that you're losing electrons, right?
Mm-hmm.
So if you lose them, then you got to be on the other side. So how many total electrons has strontium lost?
2.
How many?
4.
Or
Okay, thank you. So yes, strontium loses 2. That's correct, but you have 2 strontium. So when you do this, you got to put the total number of electrons lost in the entire reaction. Okay, cool. So then what's the form of strontium on the other side?
SR plus 2.
2.
Good job.
2. Yeah.
Yep, 2SR2 plus. Good job. So reducing half, what do I write?
O2 plus
O2 negative 2 at the top.
Nope.
it's plus
Wait, hold on 1 second. Carry on. It's not O2 negative 2 at the top. Okay, do you understand why? We're on the left side, and the left side is just oxygen gas. It's not an ion on the left side. So you don't put O2 2 negative. And first of all, you wouldn't put O2 2 negative on the right side either, because O2 denotes that it's bonded, and it's not bonded on the right side to another O. But anyway, what's the next thing after O2?
plus 4 electrons.
Correct. Then
O2 minus. Is that wrong?
It's
Yeah.
2 oxygens.
Yes, it's 2. You need to always use the coefficients. That's going to screw you up. 2O2 minus. So you have the form, right? But you got to tell me how many there are. You guys can't forget that. Any questions on this one? I mean, there's little, you guys, I think are getting it. You just little silly mistakes here and there, but for the most part, you get the protocol, right? So it's pretty easy. You just have to remember to do everything. Let's try the second one. Let's try the second one. So help me, is it balanced? If not, help me balance it.
It's balanced.
It's balanced. Okay, great. So next, what do I do?
Oxidation numbers.
Okay, so go ahead.
Lithium will be 0 and H2 will be 0 as well.
Okay, other side.
Lithium will be +1 and hydrogen will be +1. No, hydrogen will be -1.
Correct. So that's weird. But that's the first time we've seen that. So that's okay. So now lithium is who? Leo or Ger?
They're
It's Leo.
losing electrons.
Right, so it's Leo. So that means that oxygen is who? Ger, right? Gaining electrons. That means that Leo is the what agent?
Reducing.
Good job. See how it's the same? It's the same. So this is oxidizing agent. Okay. Next, half reactions. Let's go again. Let's try.
2 lithium. And that's, so then you do the arrow, right?
Yep.
And then 2E with a negative plus 2 lithium plus 1.
Good job. Finally used those coefficients. Good girl. Okay, so reduction half, somebody else, tell me.
H2
Okay.
plus 2 electrons, 2E.
Okay.
Arrow. Oh, H2. H2 negative 1.
Like this?
Yes.
Really? Let's think about that. What, okay, remember, oh my gosh, you have to put it in the form that it's in. This is what type of compound? Ionic
Atomic. Oh.
or molecular?
Which one? Oh, ionic.
Ionic, right? So is that an ion?
No, it would just be H.
So tell me how to write the correct form. It would just
It
be
was just
say the whole thing. So it would be what coefficient, what form of hydrogen?
2H negative.
2H negative 1. Okay, which this is it. Remember, these guys, these are oxidation states, yeah? And well, sorry, my bad. These are the forms that they are in, oxidation states. These are the forms that they are in. And the hydrogen, as weird as it looks, does take the reducing guy, does take the reduction part of that reaction because it's connected to a metal. So if you add all of these two guys up, you're gonna obviously cancel the electrons, and you're gonna get back to the original equation. You guys have to write the correct form. You have to write the correct form. So realize that these guys are mostly going to be ionic compounds at the end. So you've got to remember that. They're in the form of an ion. You can't put H2 because H2 is a diatomic molecule. You can't put O2 because O2 signifies that's a diatomic molecule, a covalent compound. You can't do that. So you've got to remember, if it's an ion, if it's an ionic compound, you got to put it in the correct form. Okay, so I'm going to let you guys do, or do you guys want me to do it with you, or do you want to do it by yourself and someone just tells me at the end? Let's do the third one.
So Dr. Tourné,
What's up?
lithium was being oxidized.
Leo, correct. He lost electrons. Yep. Do you guys want me to give you some time to do it on your own and you tell me? Okay, yes. All right. So do the third one. Hold on. I'm going to get something to put my computer on because I can't hold it. Anybody ready?
Not just yet.
Okay. Okay, let's start. You guys, so that's about how long it should take you to do the whole thing, just FYI. I don't know, maybe that was like 2 minutes or something. But really, it shouldn't take you longer than that because it's the same process. So is it balanced? Yep. Oxidation states. It's just so simple, right? It's the same. So magnesium is a 0, nitrogen is a 0. What's the oxidation states on the right?
Magnesium has a +2 and nitrogen has a -2.
Oh, no.
Not? Oh, no, it's -1.
No,
It's
ma'am.
It's not.
No, ma'am. So goes back to reading the periodic table. Who was talking? Was that Makai?
Yeah, oh, never mind. I remember. Is it a -3?
Why are you trying to remember? Are you trying to remember?
I was looking at my periodic table, but I had to I don't have it written at the top, but I had to remember the order. So that's why I had to remember it.
Okay. But so yeah, it's -3 because of where the dude sits on the periodic table. So simple. And if you weren't sure, you could just do the little math problem and you'll see that if you have 3 times 2, +2, that's +6, and -3 times 2 is -6. So that equals 0. Okay. So magnesium to magnesium. Who is he? Leo or Ger?
Oxidizing.
Yep, so that's Leo. And then this dude is obviously Ger. Okay. We all know this is the opposite agent. So this is reducing agent. This is oxidizing agent. Really what I'm concerned about are these half reactions because that's where you guys mess up most. So oxidation half.
3 magnesium yields 6 electrons plus Mg. Mg with the subscript of 3 and then 2 plus.
Wrong. Okay, how maybe I'm not getting through to you guys. Like, do you understand? You guys understand what subscripts mean, right? Like, do you get what a subscript is? A subscript, if you were to tell me Mg3, if you were to write that by itself, right? That's like saying O2, right? O2 is a compound that is double bonded with another oxygen. So you're saying that Mg, a metal, is bonded covalently to 2 other magnesiums, right? So 3 magnesiums are covalently bonded together. Again, what type of compound is this?
Ionic.
Right. So you don't have this. This does not exist. If you write Mg3 with a subscript, that's what you're saying. You're saying that it's Mg connected to another Mg connected to another Mg. That is not what's happening here. What's happening here is you have an Mg 2 plus connected or attracted, I shouldn't put a little line, attracted to a nitrogen, which has 3 negatives. It's an ionic, so 3 minus. So it's basically 3 of these. 3 of these. It's not Mg is connected to Mg is connected to Mg. So that's why I keep saying you have to write the correct form. You cannot do Mg3 just for the same reason that you could not do H2 in the LIH from before. You can't do that because that denotes covalent compound. That denotes that two H's are connected together. That is not what's happening here. Mg3, magnesium nitride, is an ionic compound between magnesium and nitrogen, not between magnesium, magnesium, magnesium. So you've got to tell me the correct form. Can somebody else try?
I would like to try.
Go for it.
Okay, so is it just 3 mg?
Okay.
I mean, not like
Done?
just, so yeah, so that what we have down is right so far, so it would be plus 3 mg.
But you're missing something. Is this Austin?
No suggestion.
Oh, hey, Jashawn. You're missing something. It's an ionic
Oh,
compound. Ionic compound. It's an ionic compound, so you need to have it in the form of an ion.
so it
Right?
would be plus, or 3 mg and then plus 2.
Yes, that's it. Good job. You guys, you obviously see that everyone's doing the same thing, right? Like you guys, how can I explain to you, how can I make you remember? You can't, you've got to write it in the correct form that it's in. So you look at the product and you say, well, don't forget what chapter 2, what you learned. This is an easy ionic compound. So that means that whoever makes up these things has to be an ion. If you put 3 mg, you're almost right, but you would be wrong because you're saying you just have 3 neutral magnesiums. You can't do that. That's not what it is. It's a magnesium ion. You can't do the Mg3 that other people suggested for the other reason. So you have to write it in the right form. You'll get, I mean, hopefully you guys will get this by Friday, but let's try the reduction half. Someone else want to try?
Can I retry?
Sure.
Okay, so on that part, you put 6E minus
Okay.
plus 2N minus 3.
Oh, man. No.
Ah,
Why? What form is nitrogen in the left, on the left?
oh, 0.
Is that an ion?
No.
No, it's not. So what would you put then? That's
Oh, so would I just put 2N?
no. You would just put N2 the way it is.
Oh, okay.
Because it's not a covalent compound. That is it's by itself, and that's how it exists. N2, right? It's a covalently, this is actually N1, 2, 3. It's a triple bond between 2 nitrogens. So that is how it lives in that particular compound. So for this case, no, you leave it the way it is because it's a diatomic molecule. So that is your left side. What would be the right side? Let's finish it off, Jashawn.
Oh, can you repeat that?
I just said, let's try to finish it off.
Oh, okay. Okay, so then on the right side, would it be 2N minus 3?
Yes, 2N 3 minus, because on this side, it's an ion. So therefore, and you have 2 of them. So you have to put the coefficient in front and say that you have 2 nitrogen 3 minus ions. Okay, so let's do the last one. Yeah, what's up?
For that, oh dang, for that reducing side, it said 6E minus, but wouldn't it be 6E plus because the nitrogen is the one gaining the electron?
Okay, electrons are always negative. So ixnay on the E plus. Don't do that ever again in your life. And if one dude, the nitrogen is actually gaining the electrons. Right. So electrons are not positive. So he's gaining 6 negative charges.
The magnesium.
But it's not right. And the magnesium's losing them, but the nitrogen is gaining them, but no one ever changes to a positive. You see what I'm saying? Like an electron is an electron. So I'm giving you 6 negative charges, but they're still negative. So it's not 6E plus. E plus does not exist.
Okay.
You sure? Are you sure that's okay?
Oh, yeah, I get that.
Yeah.
So I'm basing it with it just being on the other side of the yield reaction. It signifies like
You're adding it to the dude.
right.
Right. It's reacting, right? So that on the reacting side, you're adding it to the dude because they're reacting together. And the other dude lost it. That's why it was as a product. Okay, last one. Let's try to do it quickly. So obviously you guys are really good with the whatchamacall, the oxidation states and all that, but this needs to be balanced, does it not? What does it need? So I'm gonna put a 3 here. So that makes it 6. Oh. That makes it 6. So this would be a 2 and then this would be a 4. Done. Okay, great. So this is 0, this is 0, this is -2. What's the Fe on the other side? What's the oxidation state?
+3.
Okay. So who's Leo and who's Ger?
Leo is reduction. I mean, sorry, the iron is reduction.
Yes. Leo is, I was going to say the same thing you said. Leo is reduction. No, Leo is iron. And then this is Ger. This is reducing agent. This is oxidizing agent. Okay. Let's get to the stuff that you guys hate. Oxidation half. Here we go. Somebody, let's see. Let me pick somebody. Makai, do you want to try?
Yes, I'll try.
Okay, good. What's up? Tell me what to write.
So for the oxidizing half, it would be 4H2.
What?
Wait, no, hold on. I'm on the wrong problem. Whoa. Looking at the wrong problem. Okay. It would be the 4Fe.
Mm-hmm.
Then yields.
Okay.
Okay, and then I want to say, because it's 3, it's 2, how many electrons? I want to say like 6 electrons.
Come on, girl. Do your math.
I want to say, hold on.
Not 6. How many irons do you have? You just told me, right?
I have 2. Oh, 4 times 3.
There you go.
So it would be 12 electrons. Sorry, dumb moment.
Okay.
And then I want to add, make sure I'm doing this right because this is the ionic side. So 2, 4. Oh Lord, I'm all over the place. Would it be the 4Fe and then the 3 plus at the end?
Yes, good girl. 4Fe 3 plus. Good job. Okay, reduction. Somebody else. Reduction half. Anybody else? Good job, Makai. Adia, do you want to try? Or somebody else want to try?
I can do it.
Okay, go. Tell me.
All right. So 3 oxygen 2
Okay.
plus 12 E minus.
And you verified, right? Don't just write 12 because you guys got 12 here. You verified that it is 12 because this is a good little step. You're right, by the way, it is 12. But it's a good little step to kind of check that you did the math right? So do it on both sides to make sure. But yeah, you've got 6 oxygens. Each of them is -2, so that equals -12. Believe it or not, this is the step where I have caught many mistakes on my math before. So just as a little advice, do check it. All right, good. Good job. So 12 electrons, then?
Yields
Okay.
6 oxygen minus 2.
Okay, does everyone agree?
Yes.
Okay, that's it. Good job. Finally, you guys, you got it. Excellent.
I can do this.
Yeah, of course, everyone can do this. Yes, you can do this. Okay.
Quick question.
Yeah, what's up?
Okay, so on the right side, how come we didn't use coefficients and
But we did
subscripts?
we did use coefficients.
I mean, like just write it out. Like for iron, how come we didn't write out 2 Fe and then with subscript of 2?
Because for the sake, can someone explain that to him?
Ionic.
Okay, but that's not an explanation, Chloe. That's not gonna help him. Tell,
It's an Fe bonded to an oxygen, but there's 3 of that bond going on. So if you write the subscript of 2, it would be saying that it's 2 irons covalently bonded together.
excellent explanation. So wait, Tashawn, do you understand what she said?
Yes, I get it. Because if you write the subscript of iron, you're saying it's gonna be 2 irons combined.
Right.
Yeah,
So
2
you
irons
say-
bonded.
Exactly, you're saying that, and that's not what's happening there.
And then if you write just putting the coefficient of 4, you're just saying that there's 4 irons in total.
4 irons, each of them with a 3+ charge, which that's exactly what's going on there.
Right. Okay. Okay. Thank you.
You're welcome. Good job, guys. Okay, let's go to the different PowerPoint. How exciting that I have. So, okay, wait, what? Okay, wait a minute. Okay, so you know how to do redox reactions. I mean, hopefully that you understand what we just did. That's it. That is literally what you need to know to do redox problems. Now, you have to understand that there's different types of redox reactions, right? There's actually 7 different types, okay? So they're really easy because you'll be able to know that it's a redox because you can do those little oxidation numbers, right? If you see that things are changing from left to right on a reaction, then that's a redox reaction. But now you have to be able to decide what type, right? So there's really easy. There's 7 of them, but they're super simple. Maybe the last one's kind of hard, but we're gonna kind of go through them really quickly. So this is a example of a redox reaction, but see how it's all in words. So I would give you something like this. So solid zinc undergoes a metal displacement. A metal displacement is actually a type of redox reaction. You don't know that yet, but solid zinc undergoes a metal displacement when it is reacted with copper sulfate. So you actually have to write down this reaction, okay? So solid zinc, what is that? Can someone tell me what to write there?
Zn.
Yep, just Zn, and you would put ZnS, right? Because solid zinc undergoes when it is reactive of so it's reacting with copper sulfate. What's copper sulfate?
Cu2.
Right, and actually I should have said, my bad. I should have said copper 2 sulfate, my bad. So now you know. So it would be reacting with Cu, and then what's the sulfate?
SO4.
Right, like that. Now look at the actual instructions. Solid zinc undergoes a metal displacement. We've heard that displacement word before. So what does displacement means when you switch somebody, right? So zinc undergoes a metal displacement when it reacts with copper. So who do you think zinc is displacing?
Copper.
Copper.
Exactly. So what do you think the product will be?
Zinc sulfate.
It will be
Plus zinc sulfate.
It would be zinc sulfate plus what? Because things don't go away.
Copper.
Copper as a what, you think?
Ion.
As an ion, as a solid. It's going to go as a solid. So copper is a solid. So this is, I started with this even though you don't know that a metal displacement is a type of redox, but it's, so you guys can start realizing how the questions are going to be worded, right? So you should know all of this nomenclature. It's really easy if you just sit down and read and do it. Okay, but you can tell, you should be able to tell right off the bat that this is a redox reaction. When you have things alone like that, you have different oxidation states, right? So this is going to be a 0, this is going to be a 0, and then you're going to have these dudes in an ionic compound that are going to have some sort of oxidation state. if you notice, the only thing that really matters here are the metals. So this metal here would be a +2. Oh my goodness, I'm trying to write vertically and it's difficult. +2. And then this guy right here would be
-2.
Oh, did I do a wrong thing here? It can't be a -2. I did something wrong. Oh, yeah, no, this is a +2. Hold on, my bad. I was freaking out for a second. It's going from zinc. Yes, okay, that's right. That the zinc on the right side is a +2, right? So it goes from 0 to +2, and the other one goes from +2 to 0. So you can tell that's a redox. Things are changing there, right? So that's just one type of a redox reaction, and something that you'll be able to do on your own and actually create products now, like a real reaction. So anyway, let me erase my stuff. So you see this is what it is. And how do they know this stuff is aqueous? Where do you think they found this information about the aqueous for those two ionic compounds?
Solubility table.
Exactly, which you're gonna have, right? So you can do all of this by yourself. Okay, so again, this is a redox reaction because of those, obviously the difference in oxidation states. And we're not gonna do it because we know how to do this already, but this would be the oxidation half reaction, right? The zinc is the guy who's losing electrons. So that's the oxidation half. And then this is the reduction half, okay? So everyone understands this, yeah? Cool?
So we wouldn't take sulfate into any consideration when doing oxidization.
Because if you notice, if you do the oxidation states, everybody involved in sulfate, they're exactly the same from side to side.
Okay.
Oxygen is -2 on both sides, and sulfur, since it's connected to the sulfate, is going to be the same on both sides. So usually that's a trick, right? So if you see things in the same form, like a polyatomic ion on the left and on the right, it's going to be the same. That's why most precipitation reactions, right? Precipitation reactions and stuff like that, those are all the same throughout, and a lot of them are involving these polyatomic ions. So they're the same on the left. So yeah, I didn't even touch it because I knew that the only thing that was changing was going to be the dudes that are basically splitting apart and having 0 to something else. So yeah, but everyone get this whole thing? Yes, it's a kind of like a review. Okay, so we know how to do the half reactions, we know how to do the oxidizing and the reducing agents. Okay, now let's actually sit down and talk about the 7 different types. So a combination reaction is a form of redox. If you think about it, I mean, it's simple. When you're combining stuff, right? So you start with 2 things and you put those 2 things as a product. So you combine them. That's what a combination reaction is. And if you think about it, you have 2 things that are going to have maybe are 0 oxidation states, and then when you combine them, they're not going to have 0 oxidation states. So that is a redox reaction. An example of that, so yeah, that's just a general example, but example of that is when you have aluminum and bromine making aluminum bromide solution. Okay, so you can quickly tell that these look 0, 0, and then these guys here are going to change their oxidation states. So that's a type of redox. Everybody cool with that? So combination is number 1. Cool? Okay. Next one is the opposite, decomposition. So obviously you start with something and then you break it up into parts. So this will also be considered, this is also considered a redox reaction. So that's, what is that called? That KClO3?
Potassium chlorate.
Good job. So that's potassium chlorate. And what here, actually, let's do it. So what here stays the same? Listen to the question. What has the same oxidation states from left to right here?
Potassium.
Right. So that means that the 2 people that are changing here has to be oxygen, and you know it because look at oxygen on the right-hand side is 0. And then the other guy is chlorine. So that means that you would have to figure out what chlorine is in potassium chlorate. So So this is a little different than what Ariel asked about before, right? Before, let me go back, the sulfates, right? The sulfates stayed exactly the same from left to right, but not in this example. In this example, the chlorine splits up. So therefore, if you actually solve for everybody there, you would see that you get a +5 in the chlorine. And then on the right, it's going to be a -1. Okay. So any questions? So you have a combination, and then you have the opposite, a decomposition. Anybody know what the next one is?
Can you quickly just explain how you got the +5? I know you solved using the algebra that you showed us earlier, but I feel like, I don't know, I feel like I'm missing something. Like I know you put -2 for oxygen because it's in a compound, and that's one of the rules. And I know you did +1 for potassium because of its spot on the periodic table, but I know you solved for the Cl, but I'm just,
I mean,
yeah.
I don't know how else to tell you. That's it. If you solve for X, it's this added to this would be -5, but then you'd bring it over to the other side, so that would be +5.
Okay, so you said equal to 0 because it has no charge, like the whole thing.
Right.
Okay, that's the part I was missing. Thank you.
Yep, you're welcome. Any other questions? Okay, does anybody have, I mean, are you sure? Do you have any, so no questions on combination or decomposition, you're good. Okay. So the next type is combustion. Does anybody know what a combustion is? How can you tell it's a combustion?
How do you tell? Isn't it from like something with to do with like I think oxygen or something?
Right. So a combustion, the prerequisite of a combustion reaction is that you are reacting with oxygen, right? Oxygen gas. And another prerequisite, which you don't need to actually fully understand right now, but it is that it's an exothermic reaction, right? So exothermic meaning a lot of energy is created from this reaction. And that's what a combustion, I mean, if you think about the word combustion, it combusts, right? So big, huge boom, right? And that's usually, that's a prerequisite of a combustion reaction, when a lot of heat and energy is released on the other side. But for right now, is yes, it's when something is being reacted with oxygen gas. So O2, that's a combustion reaction. And also considered a redox reaction. Look how simple. S is going to be 0, O2 over here is going to be 0, and obviously the oxidation states here will change. So that's a redox. Okay. So, oh, I wrote it, I had it on the slide. Okay. Okay. There you go. So those are the oxidation states from left to right. Okay, anybody have any questions? So now we have 3 of them: combo, decomp, and combustion. Cool? Cool? Is that cool? Okay. Go ahead, carry on.
For the sulfur on the sulfur that's +4 on the right side of the reaction, you got that because of the -2 charge on the oxygen. Yeah.
You tell me. You set up a little math equation. So you would equal it to what?
Equal it to 0.
Right, so that's it. Equal it to 0. This is -2, but you've got 2 of them, so that's -4. So this is X. There you go. Yeah. Yep. So this is just another example of magnesium ribbon, and you combust it with some heat, and then what you're going to get is magnesium oxide. So obviously you can tell hopefully very easy. Oh, my bad. Hopefully, oh gosh, hopefully very easily that that's a quick redox. Okay. So we've done, let me see, decomp, combination, combustion. Now we're going to do, wait, am I missing one? What? I got to go back. Yeah, no, that's 1, 2, 3. What's the, that's right. It's at the end. Okay, so now we're going to go through 3 displacements. Okay, so we know what displacement means. I just showed you one before we started this. But there's a hydrogen displacement. Okay, so a hydrogen gas gets kicked out. There's a metal displacement, which is the example I showed you at the beginning. A metal gets kicked out and somebody else takes over. And then there's a halogen displacement. So now with those 3, we would have 6. And then there's 1 left, which is the hardest one, which is why I leave it to the end. But anyway, the next thing is, let's talk about hydrogen displacement. First, so you guys don't start freaking out. If I ask you something about a redox reaction that involves a hydrogen displacement, I will give you this chart. Okay, so this is a reduction strength chart. Okay, so obviously the people that are higher have a higher tendency to reduce. So what does reduce mean? To gain electrons, right? So they're more powerful at gaining electrons and than the people below them. And you can kind of like justify it to yourself. Look who is the strongest here. Lithium. Where is lithium?
Row 1 at the top.
It's row 1 at the top. Exactly. So lithium is a really small a really small atom. And it's so the fact that it gains, that it loses an electron, you should understand that because it's so freaking close to being a full octet, quote unquote full octet, that it's going to want to do that immediately. It's all about stability, right? So if it's way more stable over here, then it's going to do that quickly. And obviously you can kind of justify to yourself the people below it, right? So you can justify it and say to yourself, yeah, that makes sense. Barium is not as strong as a reducer than lithium because barium needs 2 of them. You need to lose 2 electrons versus the 1 electron. Okay, so it kind of goes in order, but you don't need to know everybody's strength. You just would be able to use this chart that I would give you and answer some questions. That's all. Okay, so the sections are separated by this this H2 is just here for comparison, by the way. But the sections are separated by their strength, but also to let you know that this guy, lithium, for example, is so freaking strong at losing electrons that all you got to do is drop a little bit of cold water. If you drop a little bit of cold water on lithium, it's going to immediately produce hydrogen gas. That's how strong it is, because it's going to freaking lose that thing and displace a hydrogen gas. So lithium plus water, if you're thinking about reactions, lithium solid plus water, the hydrogen gas will be expelled, because that's the whole point of this. So H2 will be expelled, and then you'll have an Li, what's left? Lithium plus water. You'll have H2, and then what is left? What's the
lithium oxide?
Right. So you can kind of start like being almost like making reactions on your own just by the words and the stuff that they give you. But that's basically what's happening. Okay, so that's what it's telling you. These guys are not as strong because you can't they won't react. If I drop cold water on a magnesium solid, because actually magnesium comes in a little ribbon. So if I drop cold water on magnesium, the little ribbon, nothing happens. But if I drop hot water on magnesium, then you'll see a little gas form. It's so cool. Like chemistry is so freaking cool. But anyway, so that's what this chart means. Okay, so I would give you, for example, something like this. If I gave you, okay, so if I had calcium and I reacted it with cold water, and I would tell you in words, if I had calcium and I reacted it with cold water, would it be able to displace hydrogen? And you should, by looking at this chart, you should be able to say, yup, because look at where calcium is. It's right here. And if I just put cold water, it's going to go ahead and displace it. And you see how hydrogen gas is created. Okay? So that's the point of this chart. Now, if I asked you for somebody else, I'd say, okay, guys, if I add cold water with lead, am I going to displace hydrogen? You would look here and you would say, no, ma'am, because PB is down here, and you need to actually, the only thing that you can actually displace hydrogen from lead is if you actually add it with an acid. All right? So everyone understand the chart? Cool? Yes? What's up?
So when you're looking, like how it goes from lithium to a lithium ion plus an electron, that electron is going to the hydrogen?
Yeah, actually, yeah, because it depends what it's being reacted to, but it's usually with water. And if it's H2O, this would be, think about it, this would be 0, this would be -2, this would be +1, and then here you've got a 0. So +1 to 0, that means you're gaining an electron, right? So yeah. All of this information you guys have now that you can answer your own questions. It's amazing. Okay, so any other questions? Because this is the first type of displacement. So this chart is actually used for another type, for metals. So the next type of displacement is metal displacement. So look, it's the same freaking chart. So a metal in a compound can be displaced by another metal depending on how strong that metal is, how strong of a reducer that metal is. So again, the higher people are stronger at reducing than the lower people. So if I said something like this, if I gave you this reaction and I said vanadium oxide with 5 whatever calcium, solid calcium, would I be able to get those products?
I don't see vanadium on the chart.
So you would, if you don't see vanadium on the chart, then what would you guess? These are the most, these are the strongest. Remember, this is, so sorry.
Yes, if those are the strongest, it's not among the strongest, and calcium is on the strongest, it'd be able to replace it.
Bam. Bam. So it's a logical, it's a logical thing to say to yourself, well, I don't see vanadium here, so I'm going to assume that yes, calcium is able to displace vanadium. So that's basically what's happening. That's it. And if I gave you something like that was both on the, you know, on the, both of them would be on the chart, you would just have to, you know, compare. Okay, well, is silver stronger than cadmium? No. So silver is not going to be able to displace cadmium. That's it. Okay. All right. So last type of displacement is halogen. This is easy because I'm not going to give you a chart. So this one you just have to know. Look at the order. Fluorine is stronger than chlorine. Chlorine is stronger than bromine. Bromine is stronger than iodine. What does that remind you of? If you look at the periodic table, right? Fluorine is up top. Chlorine is next. Bromine is next. Iodine is next. So the higher you are, the stronger you are. Okay. So fluorine is able to displace anybody of the halogens, but iodine can't displace. Bromine can't displace. Chlorine can't displace fluorine. So it's just by order. Okay. So an example of that would be something like this. If you have chlorine and it's reacting with bromine, chlorine is trying to displace the bromine. It can do that because chlorine is higher than bromine. Does that make sense? Yeah, okay. So, and that actually is a very huge industrial process for you engineers. That happens a lot. So this is a very well-known reaction. Okay, so there you go. There are the oxidation states. Now, what if I gave you this one? Is iodine able to displace bromine? Hell no, because it's the lowest one. So that doesn't happen. There you go.
I have a question.
Yeah.
Looking at you didn't put a number in front of the 2 because it's not changing? In front of the 2 potassium?
Huh? Oh, right. Yes. This is the same. +1, +1. Yep. Exactly.
Thank you.
You're welcome. So, okay. Check it out. I know we have 4 minutes, but you got to listen. So we've got 7 types of redox reactions. We've got a combination, decomposition, combustion, the 3 displacements, hydrogen, metal, halogen. And then the last one is called, and I know this is a hard word for you guys to say, but say it correctly, disproportionation. It's a freaking weird word for a weird thing. Disproportionation means when one element, and I'm about to blow your mind, one element undergoes both reduction and oxidation. So it does 2 things in one reaction. Usually the people that can do this are the people that have, remember the periodic table with that has all the states, the oxidation states that have like chlorine. Chlorine has a ton of oxidation states. It's usually people like that. Nitrogen has a bunch of them, so nitrogen is also able to do it, right? But chlorine is the most common, and that's why I have The same element is simultaneously oxidized and reduced. So for example, look at this. Let's really quickly do it. Give me some oxidation states. What's the oxidation state of chlorine here, Cl2?
0.
Yep. What's the oxidation state of oxygen here?
-2.
Okay. What's the oxidation state of hydrogen?
Positive.
What?
Positive.
Positive 1, yes. Okay, so now what is the oxidation state of oxygen in the ClO, in the hypochlorite anion?
-2.
-2, which means the chlorine is what?
1.
Positive 2.
Positive 2.
No, it's not 1. Who said 1?
Oh.
Positive 2.
It's positive 2, right? Because it's got to cancel. Okay, but look at the other chlorine. What's the other chlorine, the oxidation state?
-1.
There you go, -1. So what in the freaking hell is going on to this dude? So this dude is going from 0 to positive 2, but it also is going from 0 to -1. So that's what, go ahead.
The chlorate is negatively charged by 1. That's why that little minus is there.
Oh, my bad. You're bad. You're right. Yes, it is. So this is not a positive 2. Yes, you're right. So we would have to do the little, okay, so this is -1, this is -2. Thank you for pointing that out. So this would be what then? What's your X? Positive.
Yeah.
Right? Because we only have 2. So this is positive 1. There you go. Thank you. Good catch, dude. So that, but still, it's different, yeah? So positive 1 and -1. So he's getting both reduced and he's getting both oxidized. Again, this only happens to people that have a ton of different oxidation state possibilities. Chlorine is one of them. So you have to remember this type of redox. Even though it's weird and it has a weird name, it happens. Okay, so you gotta be really careful, especially like the mistake that I just did. Be really careful and be able to get all of the oxidation states for everybody around. Any questions? Tarion, you look like you're completely confused. Are you okay?
No, because I'm going through some technical difficulties with my computer. My screen is completely frozen. So I'm gonna do it.
Oh, okay, but you're good? Because the face that you're frozen on looks like you're stressing.
I'm frozen.
Okay. Anybody else? Does anybody have any questions? Because that's it. This is all I got. This is all I got. Let me just make sure. Yep, 0, 0. There you go. Reduced oxidation. Yep, that's all I got.
So since the chlorine is what's oxidized and reduced, everything else stays the same?
Yep. Everything else stays the same, and you can tell. Here would be oxygen is always -2, and this would be a +1. Yep. And then you would do the oxidation and reduction half reactions the same. The same. Just take, they would both start with chlorine, which is kind of cool. Cl2. Any questions? So on Wednesday, today there's a study session. Just to remind you, there's a study session. It's the last one. So they're big hurrah. Hopefully they all have boards and stuff like that. But anyway, they worked really hard on their problems. So if you guys want, you should go. It's free. And remember that I am giving you extra credit for those of you that go and interact. So that's tonight. And then Wednesday, we're doing, what are we doing? Titrations and dilutions. I'm kind of mixing them both together, but titrations and dilutions. So we've only other type of reaction that we have left. It's called a neutralization reaction. And you've seen it before, but I just haven't called it that. But it's just when you have an acid and a base and you bring them together, they neutralize. So not a redox, but that's the last type. And you've got to know everything about titrations. You got to know like all the ins and outs, the names, the whatevers, titrant, endpoint, all that other stuff, equivalence point. But they're really easy. Compared to this stuff, it's really, really easy. So, and that's it. That's it. Then it's Friday, and there you go. On Thursday, we will have, sorry, I know it's 12:02. On Thursday, the second section, I'm not having a second section because I actually have to get on a plane, which I'm super stressed out about, but I have to get on a plane. So I'm more than likely, maybe some people are going to, from the second section, are going to join us on Thursday, right? So we'll hope maybe have a bigger class, because I'm just going to record it and that'll be their class, because I can't do the second section. Anyway, all right, that's it. Cool. Good, everybody? Okay, let me stop sharing. If you guys have no questions, then that's it. You guys can go.
Have a good day.
Thank you. You too.
You have a blessed one, Dr. Tournay.
Thanks, you too, Terrion. Joshua, do you have any questions? Okay.